So the rest of section 1.3 is all about evaluating analytical limits. Analytical just means from formulas. We know how to figure out limits from graphs. We know how to figure out limits from tables of values. Now we need to start looking at what if I give you a formula. And before we start getting into a lot of this, there are three basic limits that we're going to use to build up really our kind of theory of how we deal with these analytical limits. So three basic limits. The first one, the limit as x approaches c of b. Which might not make a whole lot of sense. There's a whole lot of letters there. You know what? Let me give you a specific example of what this is kind of like. This is like saying the limit as x approaches 3 of, oh, I don't know, how about the constant function 5? This first limit is how we take the limit of a constant. What's the limit as x approaches 3 of the constant function 5? Well, I can draw a graph. What is the constant function 5, or the constant function y equals 5? It's just a horizontal line at a height of 5. As my x's get really close to 3 from both sides, my y values are getting really close to 5, which actually would be the same thing if I was getting really close to 2, or -1, or 1,000, or anything like that. This limit is just going to equal 5. So in general, if I want to do the limit as x approaches c of some constant, it's just going to equal whatever that constant is. Number 2, the limit as x approaches c of x. Again, there's like a lot of letters here. Let me try to give you a specific example. Let's do the limit as x approaches 4 of the function x. Okay, well the function x, y equals x, that's a slanted line with a slope of 1 that passes through the origin. So let me try to graph this. As my x's get close to 4, my y's are also getting close to 4. That's sort of how the function y equals x looks like. So what's the limit as x approaches c, some other x value, of the function x? Well, that's just going to equal c. One more. The limit as x approaches c of x raised to the n. Like thinking about the limit as x approaches 6 of x squared. Well, I know that y equals x squared is a parabola, and I know parabolas are continuous everywhere, so at x equals 6, whatever you're approaching from the left and the right is the same as what the function is going to equal. I'm just going to go and plug in 6. I'm just going to get 6 squared. That limit's going to be 36. So in general, it's going to give me c raised to the n. If you need a little bit more time to copy these down, make sure you're pausing the video. But what we can do with these basic limits and our properties is figure out how to evaluate limits where a function is continuous. Or rather, these things let us evaluate limits in places where a function is continuous. So that's the next case we're going to look at. And by the way, the story for the rest of this unit is going to be how to figure out limits from formulas where a function is continuous, where there's a hole, where there's a jump, where there's an asymptote. We're going to go through all those different cases and see how to work with formulas if I'm not just looking at a graph or a table of values. Evaluating limits where a function is continuous. Let's see, I've got some function over here that's continuous. Well, if I want to find the limit as x approaches c of some continuous function, If it's continuous, that limit has to be the same as the value of the function right there. So really, instead of figuring out the limit, I could just find f of c, and they're going to be the same thing. All I need to do to evaluate a limit where a function is continuous is just plug in. Why am I allowed to do that? Well, because of those three basic limits we just went through and our properties that you saw in that last video. I'm going to show you one example completely done out with all the property work and stuff, but then I'll show you the much simpler work you're going to end up showing me. Let's take a look at the limit as x approaches 3 of x cubed minus 4x plus 1. By our properties of limits, I could rewrite this problem as the limit as x approaches 3 of x, that thing cubed, actually I guess I could leave the cube inside, but whatever, let me keep going, minus 4 times the limit as x approaches 3 of the function x, plus the limit as x approaches 3 of the function 1. How do you figure out the limit as x approaches 3 of x? Well, by our second of three basic limits, I know I can just plug in that number to where the x is, and I'm just going to get 3. I'm going to say 3 cubed minus 4 times limit as x approaches 3 of the function x is again 3, plus limit as x approaches 3 of the constant function 1 is 1. We're going to get 27 minus 12 plus 1. That should end up equaling 16. This is why the answer is 16, but the work I need to see is truly just your plugging in line. Show me how you're plugging in 3 and getting 16 for an answer. Let's take a look at the limit as x approaches 1 of 2x plus 1 over x minus 2. I would like you to go find that limit. Don't bother with using the properties. Just plug in and get a limit out of this. I do need to see the plugging in work, but you should be getting negative 3 out of that. What about the limit as x approaches 3 of the cube root of 2x squared minus 10? See what you can do with that one. Cube root of 8, which is 2. I hope you're realizing these are not super difficult. If our function is continuous, you're just plugging in. And you definitely know how to plug into functions. 2 more. Let's do the limit as x approaches pi of the tangent of x. Well, I know tangent has asymptotes, but they're not at pi. They're at pi over 2, negative pi over 2 and stuff, so I'm just going to say the tangent of pi. At this point, you'll either draw out some triangles or use some unit circle ideas. To me, unit circle stuff is a little bit easier to think about, so I'm going to use my unit circle and figure out the sine of pi divided by the cosine of pi. Sine of pi is 0, cosine of pi is negative 1. That limit is just going to be 0. One last one. You try this one. Limit as x approaches pi of the sine of 2x over 3. Try that one. Let's see, it's the sine of 2 pi over 3. Again, either draw out your right triangle in quadrant 2 or think about how the unit circle works, but your sine should end up being root 3 over 2.